All right, today we're going to tackle one of the absolute biggest challenges in the blockchain world, scalability. See, everyone's chasing this dream of a stateless blockchain, but it turns out there's this fundamental trap hiding in plain sight. So we're going to break down exactly what that trap is and then explore a fascinating new way to escape it completely. So let's just jump right in with a huge question. What if this whole multi-billion-dollar quest for a super scalable, stateless blockchain, what if it's all built on a premise that's mathematically impossible? It's a huge thought, right? And it's at the very core of what we're digging into today. Okay, so first things first, let's set the scene here. Why is everyone so completely obsessed with this idea of statelessness anyway? Well, it all comes down to the dream of what a truly scalable digital world could actually look like. Look, the goal here is actually super simple, but really powerful. In a stateless system, the people who secure the network, the validators, they wouldn't need to store the entire history of every single transaction. This would make running a validator way cheaper and way easier, which means more people could participate. And that leads to a more decentralized, more secure, and way faster network for all of us. It's really the holy grail. But, and this is a big but, here's where we slam into that hidden wall I was talking about. It's a deeply technical but unbelievably important issue called the witness refresh problem. And it basically threatens to stop that whole stateless dream right in its tracks. To really get this, we need to know what a witness is. Think of a witness as your personal digital proof for a specific transaction. It's the bit of data that proves you actually have the money to send, or that you really own that digital collectible. Here's the crazy part. In a lot of these systems, whenever the global state of the network changes, meaning whenever anyone on the network does anything, your proof can just, poof, become invalid, and you're forced to constantly go back and get a new one. Here is a fantastic way to think about it. Imagine you're a student in this huge, massive school, and even if you're at home, sick in bed, you still have to trek all the way to school just to check this one super messy bulletin board every single day, just on the off chance there's an update that might affect you. It's a huge, constant pain, right? Especially if you're not even doing anything. Well, that's the witness refresh problem in a nutshell. And look, this isn't just some annoying little quirk. It's literally a mathematical law. The Christ-Bono impossibility theorem, which came from researchers at A16Z Crypto, formally proves it. Basically, it proves that in any system built this way, the number of people who have to refresh their proofs just keeps growing and growing with network activity, even if most of those people are totally inactive. You just can't optimize your way around it. It's a fundamental wall. So if the problem is basically baked into the math, what have most projects done? Well, for the most part, they've just accepted it. They've treated it like a law of physics and have tried their absolute best to work within its constraints. This is what's known as the global state trade-off. And this whole problem comes from the way most blockchains are designed, using something called the Global Succinct Commitment Model, or GSCM for short. In this model, the entire massive state of the blockchain gets compressed down into one single tiny piece of data, a root commitment. Think of it like a single unique fingerprint for the entire database at one specific moment in time. So here's how it works. It's pretty simple. 1, you've got this one single giant global state for everything and everyone. 2, the validators, the guys securing the network, they only need to keep track of that one tiny root representing the whole thing. But, and here's the kicker, 3, for you to do anything, your proof, your witness, has to be checked against that one single root, which is changing all the time. And you've definitely heard of systems that use this model. Rollups are a perfect example. Now, don't get me wrong, they're brilliant innovations. They do an incredible job of cutting down data costs and making things way more efficient. But because they're still built on that single global commitment, they're ultimately still bound by that same exact witness refresh trade-off. They're playing the game much, much better, but they're still playing the same game. So, what if you could just change the rules of the game completely? This is where things get really interesting. The paper we're looking at introduces a totally radical new way of thinking, a local-first model that just throws the old assumptions out the window. So, what's the solution? What's this big, game-changing idea? It's actually deceptively simple. Eliminate the global state commitment. Just get rid of it, the whole thing. And this just lays it out perfectly. On the left, you've got the old way, the global commitment model. One root for the entire world. Any activity from anyone can mess with your witness. But look at the right, the relationship local model, or PRLSM. Here, you only have local roots for your relationships. If two people you don't know do a transaction on the other side of the world, it has zero effect on you. Absolutely none. Okay, so the fancy name for this new architecture is a partitioned relationship local state machine. It sounds complex, but the idea is actually quite simple. Instead of one giant single state, you partition it. You break it up into all these separate little chains for each relationship between users. So verification doesn't happen against some global thing, it happens locally, just between the people involved. And this is the really elegant part, the genius of it. This model doesn't break the impossibility theorem. You can't just break math, right? No, it just sidesteps it. It completely avoids it. By getting rid of that single global commitment, it's operating in a totally different playground where that theorem's rules just don't apply. It's like avoiding a traffic jam by taking a helicopter. Okay, so that's the theory. It's super clever, but what does it actually mean for you, for me, for the average user? What's the real-world payoff here? Let's break down the two paths. Man, this table just says it all, doesn't it? Look at the inactive user burden. In the old global model, you're constantly having to update stuff. In the new local model, zero. Zero updates for activity that has nothing to do with you. What about doing things offline? The global model needs you to be online for verification. The local model, it actually supports offline finality between two people. And the economics, your costs are tied to your activity, not the fire hose of everyone else's global activity. It's a game changer. I just want to pause on that for a second. Zero. The number of times you, as an inactive user, have to do anything because of what other people are doing is zero. That's not just a little better, that is a fundamental shift in how we think about user experience and the entire economy of a network. So when you pull all of this together, this new model really forces us to take a step back and rethink what a scalable future could actually look like. It kind of suggests we've been laser-focused on optimizing the wrong part of the problem all along. Okay, so let's just recap the absolute key breakthrough here. That big impossibility theorem, it only applies to systems with a single, succinct global state. This new model, the PRLSM, avoids that trap by just eliminating that global commitment. So verification becomes a local thing, happening just within specific relationships. And by doing that, it creates this clean separation, a complete escape from that nasty witness refresh problem. And that brings us to the final big picture question. For years, pretty much the entire industry has been obsessed with optimizing a global state, making it smaller, faster, cheaper. But maybe, just maybe, the real breakthrough isn't about optimizing at all. Maybe it's about partitioning. Is breaking the problem apart, instead of trying to shrink it, the real key to finally unlocking a truly decentralized and massively scalable internet for everyone? It's a pretty powerful thought to end on.